What happens when an invention works, but the world is not ready to accept it? We often tell the story of progress as if it moves in a straight line. A scientist discovers something. The evidence is convincing. The invention spreads. Life improves. But history is rarely that generous. Some ideas do not disappear because they fail. They disappear because they arrive at the wrong moment, threaten the wrong market, or ask society to change faster than it wants to. This is the story of forgotten possibilities. Living medicines, plant-based materials, self-healing buildings, ocean power, immune therapies, safer reactors, and transport systems that once seemed ready to reshape daily life. Some were incomplete. Some faced real technical problems. Some were surrounded by claims that still deserve caution. But all of them reveal the same pattern. A solution is not judged only by whether it works. It is judged by whether it fits the world that already exists. And when it does not fit, even a breakthrough can become a footnote. So the question is not simply, why did these ideas fail? The deeper question is more uncomfortable. How many futures have we left behind? Not because they were impossible, but because they were inconvenient. Before antibiotics ruled medicine, doctors were already fighting bacteria with viruses. They were called bacteriophages, tiny viruses that infect and destroy bacteria. Unlike broad antibiotics, phages were precise. A doctor had to identify the harmful bacteria, then match it with the right phage. In the 1920s and 1930s, researchers in Europe and Georgia explored phage therapy for infections that could otherwise kill. Reports described wounds healing, dysentery improving, and patients recovering when few options remained. The idea was elegant. The treatment multiplied where the bacteria lived, then faded when the target was gone. But then penicillin changed everything. Antibiotics were easier to mass produce, easier to store, and easier to prescribe. They did not require the same careful matching. They fit perfectly into the modern pharmaceutical system. Phage therapy did not vanish completely. It survived in places like Georgia and Poland, but in much of Western medicine, it became a forgotten path. Now antibiotic resistance is forcing doctors to look again. The old tool is returning, not as a miracle, but as a serious possibility. And it leaves us with a sharp question. Did medicine move on because phages were weak, or because antibiotics were easier for the system to understand? In 1941, Henry Ford showed a car panel that did not behave like steel. It was made with plant-based fibers, including hemp, bound into a composite material. Ford struck it with a tool to demonstrate its strength. The panel resisted the blow. This was not just a publicity stunt. Ford believed farms could feed factories. Crops could become fuel, plastics, and parts. Cars might one day come not only from mines and oil wells, but from fields. The promise was powerful. Lighter materials, less rust, renewable sources, and a different relationship between industry and agriculture. But the timing was terrible. Hemp cultivation became legally restricted in the United States. World War II shifted manufacturing priorities. After the war, petroleum plastics expanded quickly. Oil, chemicals, and mass production created a supply chain too powerful to ignore. The plant-based car did not become the future. It became a memory. Today, as companies search for biodegradable materials and lower carbon manufacturing, Ford's experiment feels strangely modern. Maybe some inventions are not ahead of their time because they are unrealistic. Maybe they are ahead of their time because the world has not yet admitted the cost of the alternative. What if one answer to malnutrition grew on a tree? Moringa is not dramatic to look at. It is a fast-growing tree found across tropical regions. But its leaves are rich in nutrients, and its seeds can help clarify dirty water. For communities facing vitamin deficiency and food insecurity, Moringa offered something rare, a local solution. It did not require a factory. It did not need a complex supply chain. A village could grow it, harvest it, dry the leaves, and add them to food. Aid workers and researchers studied its potential. Some programs reported improved nutrition and healthier children. The tree also had other uses: animal feed, oil, fuel, and water treatment. But local independence is complicated. Large aid systems often rely on ongoing programs, imported supplements, and measurable distribution. Companies discovered Moringa as a premium health product for wealthy consumers. Regulations, funding shifts, and market interests changed the story. The tree never disappeared. It still grows. People still use it. But its broader promise remains unevenly fulfilled. Moringa teaches a quiet lesson. Sometimes the most powerful solution is not the most advanced one. Sometimes it is the one that gives people control. And that may be exactly why it struggles to scale. A bridge begins to crack long before it falls. Water enters. Steel rusts. The seasons do their work. What begins as a thin line becomes maintenance, then danger, then replacement. Self-healing concrete tried to change that story. Researchers in the Netherlands developed concrete containing dormant bacteria. When water entered a crack, the bacteria awakened and produced limestone, sealing the damage from within. The idea was simple and beautiful. Build the repair system into the material itself. Tests showed promise. Cracks closed. Structures could last longer. Maintenance costs could fall. The environmental benefits were just as important because cement production is a major source of carbon emissions. But construction does not usually reward long-term thinking. Self-healing concrete costs more upfront. Contractors often compete on the lowest initial bid. Building codes move slowly. Insurers want certainty. Entire industries depend on inspection, repair, and replacement. So the material exists, but it has not transformed construction at the scale once imagined. The problem is not only technical, it is philosophical. Do we want things that last? If lasting means fewer contracts, fewer repairs, and less repeat business? A crack in concrete is visible. A crack in our incentives is harder to see. A field can look alive while slowly losing its strength. Modern farming often feeds plants with nitrogen, phosphorus, and potassium. These are essential. But soil is more than 3 nutrients. It is minerals, microbes, roots, water, and time. Some agricultural thinkers argued that depleted soil could be restored with finely ground rock dust. The idea was to return a broad range of minerals to the land, the way natural weathering does over centuries. Farmers who used mineral amendments sometimes reported healthier crops, better yields, and stronger resistance to pests and drought. The method was appealing because it could be cheap. Rock dust was often a byproduct of quarrying. It did not need a complex chemical factory. But chemical fertilizers had advantages that markets understood. They were standardized, concentrated, measurable, and profitable. They produced fast results and fit the industrial model of agriculture. Rock dust remained on the margins. It is not a universal cure. Results depend on soil, climate, crop, and mineral source. But the larger lesson still matters. Soil is not just a container for plants. It is a living system. And when farming treats land like a machine, eventually the machine begins to forget how to live. The ocean stores sunlight in layers. Warm water rests near the surface. Cold water waits far below. Between them is a temperature difference that can be used to generate power. This is the idea behind ocean thermal energy conversion, or OTEC. Warm seawater vaporizes a working fluid. The vapor turns a turbine. Cold, deep water condenses it back into liquid. The cycle repeats. Unlike solar or wind, OTEC can run day and night in tropical oceans. It also has possible side benefits: desalinated water, aquaculture, and energy for islands that rely on imported fuel. In the late 20th century, pilot projects showed the concept could work. Then momentum faded. The technology faced real obstacles: deep water pipes, corrosion, storm-resistant platforms, and high upfront costs. But it also challenged existing energy systems built around fuel extraction, centralized grids, and familiar infrastructure. Research continued, but large-scale deployment never arrived. OTEC remains one of those ideas that seems to wait just offshore, proven enough to be intriguing, difficult enough to be delayed. The ocean still holds the same temperature difference. The question is whether we have enough patience to build for a future that does not pay back immediately. More than a century ago, one doctor noticed something strange. Some cancer patients seemed to improve after severe infections. Their fevers rose, their immune systems awakened, and sometimes tumors shrank. Dr. William Coley believed the immune system could be pushed to fight cancer. He developed bacterial toxin treatments designed to provoke a strong immune response. Some patients had remarkable outcomes, especially with certain tumors. But the treatment was difficult to standardize. Dosage depended on the patient. Responses varied. The science of immunology was still young. Then cancer treatment moved in another direction. Radiation and chemotherapy became dominant. They were easier to protocol, teach, measure, and industrialize. Coley's work faded from mainstream oncology. Decades later, modern immunotherapy changed cancer medicine. Checkpoint inhibitors, engineered immune cells, and targeted treatments showed that the immune system could indeed become a weapon against cancer. Coley was not right about everything. His methods were imperfect. His evidence does not meet modern standards in every case. But his central intuition survived. The body was not just a victim. It could also be an ally. His story reminds us that some ideas are not wrong. They are early, messy, and waiting for science to catch up. A sheet of carbon 1 atom thick should not sound powerful, but graphene does. Researchers have studied graphene-based membranes for water filtration and desalination. In theory, water molecules can pass through carefully engineered pores, while salts, bacteria, viruses, and contaminants are blocked. The promise is enormous. Clean water from seawater, safe drinking water from polluted sources, lower energy costs than traditional desalination, a technology that could change life in dry regions, coastal cities, and communities without reliable infrastructure. Laboratory results have been exciting. But the world outside the lab is harsher. Membranes must be made consistently at large scale. They must resist fouling. They must last. They must compete against existing systems with contracts, facilities, and political support. So progress has been slower than the dream. This is often the hidden valley between invention and impact. The breakthrough is real, but the pathway is expensive, technical, and crowded with interests. Water is not just a resource. It is health, agriculture, migration, and power. A better filter cannot solve everything, but it can expose something important. Scarcity is sometimes natural and sometimes designed. The difference matters. In a laboratory in Tennessee, another nuclear future once ran quietly. At Oak Ridge National Laboratory, engineers operated a molten salt reactor experiment in the 1960s. Instead of solid fuel rods under high pressure, the reactor used liquid fuel dissolved in salt. The design explored advantages that still attract attention today: lower pressure, strong passive safety potential, high temperatures, and the possibility of using thorium in future fuel cycles. Thorium is abundant. Certain thorium reactor concepts may produce less long-lived waste and reduce some proliferation concerns compared with conventional nuclear systems. The experiment worked. Engineers learned from it. Then the program ended. Why? Partly because nuclear development is expensive and difficult. Partly because conventional uranium reactors already had momentum. They had supply chains, government support, licensing pathways, and military relevance. Thorium and molten salt systems were left behind. They were not magic. They had real challenges: materials corrosion, fuel processing, regulation, and public trust. But they represented a different path. Today, companies and governments are studying these ideas again. That return is revealing. Energy history is not simply a contest between good and bad technologies. It is a contest between entire systems. And sometimes the system with the most momentum wins before the better question is even asked. Imagine traveling through a city without traffic. Not in a car, not on a train. but inside a capsule moving through a sealed tube, protected from weather, guided by electric force, slowed by almost no air resistance. Pneumatic and vacuum tube transport has fascinated engineers for generations. Small versions moved messages, money, and documents. Larger visions imagined people and cargo traveling quickly through underground or elevated tubes. The appeal was obvious: speed, efficiency, automation, and relief from congestion. Some prototypes and serious proposals suggested that such systems could transform commuting and short-distance travel. But transportation is never just engineering. It is oil demand, car sales, airline routes, highway funding, real estate value, labor agreements, zoning, and public trust. A new system does not enter an empty world. It enters a world already owned, paved, financed, and defended. Modern Hyperloop proposals revived the dream. They also revived the same difficulties: cost, safety, land rights, regulation, and confidence. The idea remains powerful because it asks us to imagine movement differently. Maybe the future is not only faster engines, maybe it is less friction, less waiting, less waste, less distance between where people live and where their lives can happen. The pattern is not one secret hand stopping progress. It is something quieter. 1,000 practical reasons can slow a powerful idea. The trial is too expensive. The code does not allow it. The first cost is too high. The product cannot be patented. The supply chain is already built. The old industry has lobbyists. The new idea needs patience, and patience is hard to finance. This is how possibilities fade. Not always through conspiracy, often through convenience. A treatment that must be customized struggles in a system built for standard drugs. A material that lasts too long threatens repair markets. A crop that gives communities independence may not attract centralized funding. A power source with high upfront cost loses to familiar fuel. These are not simple stories of good inventions and bad institutions. Regulation can protect lives. Skepticism can prevent false hope. Markets can scale useful ideas, but systems also defend themselves. They reward what fits. And the future often belongs not to the best idea, but to the idea that can survive the machinery around it. Every era leaves behind unfinished futures. Some are stored in archives. Some survive as prototypes, photographs, technical papers, or memories from people who once believed they were standing at the edge of a new world. Not every abandoned idea deserved to win. Some were too costly. Some were too early. Some were less proven than their champions believed. But forgetting them completely is also dangerous. Because old experiments can contain seeds. Phage therapy returns when antibiotics weaken. Soil restoration returns when land is exhausted. Immunotherapy returns when cancer science matures. Plant materials return when plastic waste becomes impossible to ignore. Alternative reactors return when energy questions become urgent again. History is not a graveyard of failed ideas. It is a library of unfinished conversations. The challenge is to reopen those conversations with discipline, not blind belief, not cynicism, evidence. The most useful question may not be, was this invention suppressed? It may be, what conditions would allow this idea to be tested fairly today? That question is less dramatic. But it is more powerful, because it moves us from suspicion to responsibility. So what happens when an invention works? Sometimes it changes the world. Sometimes it waits. It waits for new evidence, new tools, new crises, new economics, or new courage. It waits until the old system weakens enough for another path to appear. The stories we have followed are different. Some are medical, some agricultural, some industrial, some energetic. Some are still experimental. Some are already returning. But together they reveal one human truth. Progress is not only discovery. Progress is adoption. A breakthrough must pass through fear, money, law, habit, and power before it reaches ordinary life. And at every gate, it can be delayed. That does not mean hope is foolish. It means hope must be organized. We must ask better questions. We must measure long-term value, not only short-term cost. We must make room for local solutions, durable materials, cleaner energy, and technologies that reduce dependency rather than deepen it. The future may not arrive as something entirely new. It may arrive as something remembered. An idea once set aside, a question once dismissed, a door once closed too early. And when that door opens again, we may finally discover that some of the future has been waiting for us all along.